Determine whether vector B is parallel to vector A. Remember, two vectors are parallel if they can be expressed as scalar multiples of each other. Remember that scalar C multiplied to vector A will have the effect of either stretching vector A, shrinking vector A, or rotating vector A. Or it could be even a stretch and a rotation. Now, if the scalar value has a magnitude greater than 1, then we know that vector B is longer than vector A. If the scalar value C is a value between 0 and 1 in magnitude, then vector B will be shorter than vector A. If vector B is opposite the direction of vector A, then that scalar value will end up being a minus sign. So we could summarize that like this. If the absolute value of the scalar C is greater than 1, then we know that vector B will be longer than vector A. If the magnitude of the scalar C is a value between 0 and 1, then vector B will be shorter than vector A. If C is a value less than 0, then vector B will be opposite of vector A. So our task is to just see if a scalar value C exists such that this relationship B equals C, A vector, is true. Now, if we were to expand this out, that would correspond to vector B having components B1, B2 is equal to C times the x component of vector A and C times the y component of vector A. So what this gives us is really two equations that we are going to have to check. The x component of vector B has to be equal to the scalar multiple of the x component of vector A. Also, the y component of vector B has to be equal to the scalar multiple of the y component of vector A. So we're going to independently solve these two component equalities to determine the value of C. And if the value of C is the same for both components, then we know vector A and vector B are parallel. So let's go ahead and do that. So from these two expressions, we would see that C must be equal to B1 over A1. But we also see over here that C must be equal to B2 over A2. So what we want to show is that C is equal to B1 over A1, and that has to be equal to B2 over A2. If this isn't true, then those two vectors are not parallel. So let's go ahead and plug in our values for that. So the x component of vector B is equal to minus 3/2. The x component of vector A is equal to 3. The y component of vector B is equal to 1. The y component of vector A is equal to minus 2. So what this gives us is, well, let's do some simplification. So on the minus 3/2 over 3, I see I could cancel out the 3. What I have here now is that C is equal to minus 1/2. That's from just the x components. And then we have c equal to the same value of minus 1/2 from the y component. So we have the scalar multiple c is equal to minus 1/2. Now what this means is, since c is a value, since the magnitude of c is a value between 0 and 1, we know vector b must be shorter than vector a. And also, since the scalar c is a value less than 1, we know vector b is not only half as long as vector a, it's also in the opposite direction. So let's graph vectors a and b to see what this looks like. So remember, vector b is the vector with components minus 3/2, 1, and vector a is the vector with component of 3 minus 2. We found that c is equal to minus 1/2, and that means then vector b is equal to c times vector a, because it's a scalar multiple, and that's equal to minus 1/2 vector a. Let's go ahead and sketch this out now. So I will choose a rectangular coordinate system. The vertical axis is the y-axis. The horizontal axis is the x-axis. My scale will correspond to 5 divisions is equal to 1 unit. And now we see, so let's look at vector b. Vector b has component of minus 3/2. That's going to be the x component, and 1 for the y component. So minus 3/2, that's the same as 1.5. So that's minus 1.5 on the x-axis and 1 along the y-axis. So that puts vector b right around there. So I will label this as vector b. Now vector a has an x component of 3 units, come out 3 units, y component of minus 2, come down minus 2. And I will label this vector a. So notice how vector a and vector b are in opposite directions. And so I could take vector a and kind of move it. Notice how, we would call this anti-parallel. So vector a and vector b do lie along the same line. Earlier I said parallel, but probably more precisely we would say these two vectors are anti-parallel. They are opposite in direction. And notice vector b, it takes 2 vector b's in magnitude to equal the length of 1 vector a. So you can see that from this diagram. So we have just shown that yes, in fact, vector b is a scalar multiple of vector a, and we know that it is opposite in direction.